Okay, welcome back. And let's talk about one another important function for Laplace transform, which is impulse function. Okay, before starting impulse function, we have to understand about impulse. What is impulse? It's kind of just it was zero impulse. Ah, drawing like it. So let me try again. Nothing but impulse, right? So this is impulse, okay? So we would love to talk about this kind of like, situation with mathematical function, okay? So basically, like think about it. If you like with this impulse, if I say this impulse function as g, then integral from minus infinity to infinite with this function can be written by like this simple form, because it is easy, right? Like we assume like that impulse happen at t equal to t0, then other values are zero. That's why you don't have to worry about any area except like t0. Okay, but like even like it happened. Okay, for example, like think about like what situation will happen, which is like force of large magnitude that act over very short time. It's kind of like thunder, right? Boom, right? But when I came to Texas, like I was really surprised because like in New York, the thunder is just like one line. Okay, it could be just right, but like from top to bottom, right? But like in Texas, the thunder was happening boom, boom, something like that. Okay, so like it was really beautiful. So like I was stay outside to take the photo of that thunder, lightning for a while, but it was really beautiful. Okay, but anyway, we assume like it is happened like from the top to bottom. Well, actually, scientifically, the thunder, I mean lightning, happened from the ground to sky and return. Okay, but like we are like, this is not a science course, but this is like math course though. But anyway, like that happened. Okay, so just like a one shot of thunder to the ground. Okay, then like that moment, but it is really short, but like it's not the one moment, but there is the period. That's why we would love to use like a t0 minus tau and t plus tau. Does it make sense? So this property is obvious, right? Now let me try to uh, uh, express this kind of impulse situation in math. Okay, to do so, I have to introduce one important function, which is this sub tau. It is defined here. Is okay. So well, it looks a little bit complicated, but like it's really easy. Okay, we assume that thunder or like impulse happen at t equals 0. Then let me give you the graph of this. Okay, then everything will be easy. Here we go. Okay, then if I say like a tau is like a little bit big size, minus tau and plus tau. Okay, then the height is 1 over 2 tau, right? Let's say this is 1 over 2 tau point. Then your graph is like it was 0 before minus tau, but at this point that happened, and then gone. Does it make sense? Okay, but important thing is the area under the curve. Okay, think about area under the curve. I'm talking about this area. What is that? The base is 2 tau, the height is 1 over 2 tau, which is equal to 1. Okay, but interesting is even like tau is like really big, right? But even this tau is like getting smaller, smaller, smaller. Then what happened? The height will be getting higher and higher, higher. Something like that. Even this is like minus tau tau with different tau value. The height is still 1 over 2 tau. Then the area is still 1, right? So to define the Dirac delta function, or we just simply say like delta function, like we have to have like this property. So let me introduce like the property for Dirac delta function. Okay, here we go. First of all, this kind of like impulse part. Okay, this part represent impulse, right? And that happen when t equals 0, like there is impulse, but otherwise it's equal to 0. And also satisfy like integral from minus infinity to infinite with delta function must be equal to 1. Does it make sense? Okay, it is really narrow, but height is like high enough to make like eta equal to 1. Does it make sense? But so like to define my delta function, or the impulse function g, we can send your tau 0, which means we try to make it as thin as possible. Okay, this is a way to define the direct delta function. Okay, if you want to say like that impulse had was happen at time t equal to 0, then we can use this notation, delta of t minus t0. Okay, well, like it is not easy to understand like the meaning of like this one, but as long as you understand like this direct delta function represent the impulse at time t equal to t0, and that's enough, I think. Okay, and like we would love to talk about how we can solve a differential equation with direct delta function on your right hand side as a first term. Okay, and that's it. That's the important part. Okay, so after this one, we're gonna talk about um, Laplace transform of your direct delta function. Okay, it is given here. Okay, and you can find this one on table number 17. And it's like this is like kind of like combined with number 13 and 17. Okay, so well, we're gonna use this one to solve the problem. But actually, like to derive this one, we have to use some property and mathematical um, techniques with definition of Laplace transform. But like it is a little bit complicated. So like if you are interested in, you can ask me, or you can just like read the textbook. Then everything's there. Okay. I would love to more than welcome to come to me to discuss about this one. I can explain about this. Okay. But in this video, we're gonna skip that part. But keep that in mind. You have to know like this Laplace transform of direct delta function. Okay, but keep that in mind. I'm not going to ask you to derive this one, but you have to practice how you can use this one. Okay, it is in table number 17. Okay.